Today we are going to discuss about two important topics, that is device sizing and body effect. So if you remember, in the previous lecture our discussion ended with this thing. We had made a point that so we are told that one of the expectations from CMOS logic family is that it should give at the output rise time equal to fall time, right? But what we observed in the simulation done in microwind is that when we made a CMOS inverter using a PMOS whose size was 5 and an NMOS whose size was 5. That means when the relative sizes of PMOS and NMOS is equal to 1, then we actually saw that the rise time was coming to be 3 picoseconds and fall time was coming to be 1 picosecond, which is not desirable. So basically when we use equal size MOSFETs in pull up and pull down logic, then we are not able to achieve the desired expectations from CMOS logic family. And what are the reasons why we do not get equal rise and fall times, that we are going to discuss today. So what is the need of device sizing? Okay, so we can put down some facts. That fact is, when I build a CMOS inverter using equal sized PMOS and NMOS, I get T rise not equal to T fall in the output voltage waveform. Okay, and one of the merits of CMOS logic family over bipolar logic family is comparable rise and fall times. So we should note that T rise is equal to T-fall only if the concept of device sizing is applied. Okay. So if a question is asked that is rise time and fall time equal in CMOS logic family, the answer is both yes and no. The answer is no if we use equal size MOSFETs in pull up and pull down network, and the answer is yes if we apply the concept of device sizing. Okay, that means we have to make the sizes of PMOS and NMOS unequal. So there will be mathematical analysis involved in this topic. That is why we have to frame certain terms. Okay, so for that, first and foremost, we have to draw the transistor level schematic of a CMOS inverter. Okay, so here consider a CMOS inverter which uses PMOS and NMOS with sizes small p and small n respectively. Okay. Size of MOSFET is equal to width upon length. Okay, this is very important. Okay, so therefore P is equal to size of PMOS is equal to width of PMOS upon length of PMOS. N is size of NMOS, which is equal to width of NMOS upon length of NMOS. Okay, fine. Now another important fact is for any given technology or foundry or process, with value L nanometers, LP equal to Ln equal to L. This is very important relation, especially when you want to solve numericals. Okay, so for any given technology or foundry or process with value L nanometers, the length of PMOS is equal to length of NMOS is equal to L. Okay, this fact has to be noted. Okay. consider the schematic of CMOS inverter. Okay, so here we have one PMOS and one NMOS, and here the only difference is that now the inverter is driving a capacitive load CL. So CL is a load capacitance now. Otherwise, everything else remains the same. And okay, here we will write down that the size is P equal to WP by LP, and here the size is N equal to Wn by Ln. Okay. Now we also assume that the PMOS device offers a resistance RP in on condition. Okay, so we'll write down, let RP be the on state resistance of PMOS, and RN be the on state resistance of NMOS. Okay, so that means if you want to draw the equivalent circuit of this inverter with Vin equal to 0, then we have to replace the PMOS with RP, and we have to replace NMOS with open circuit. Similarly, where Vin is equal to 1, we have to replace PMOS with an open circuit, and we have to replace NMOS with RN. Okay, fine. So consider the equivalent circuits of CMOS inverter with Vin equal to 0 and Vin equal to 1. So here when Vin is equal to 0, we can say that PMOS equal to on, NMOS equal to off. Similarly, Vin equal to 1, PMOS equal to off, NMOS equal to on. Okay, that means we can say that PMOS is replaced with resistance RP and NMOS is replaced with open circuit. Similarly, for Vin equal to 1, PMOS is replaced with open circuit and NMOS is replaced with RN. Let us draw the circuits now. For Vin equal to 0, okay. So for Vin equal to 0, PMOS is on, so we replace the PMOS with the resistor RP on-state resistance and NMOS with open circuit. And for Vin equal to 1, because NMOS is on, we replace NMOS with on-state resistance RN and PMOS with an open circuit. Naturally, it's very simple now that the capacitance will start charging towards VDD through RP. So we can actually show it like this, that the capacitor will start charging towards VDD. And here once it is charged, then when Vin equal to 1, that time the capacitor will now discharge towards VSS. Okay, so very natural, you are in final year, you know that the capacitor CL will charge towards VDD with a time constant RP into CL. Okay, so here we can say that the time constant tau P is equal to RP into CL, while the discharge time constant tau N is now equal to Rn into Cl. Okay, fine. Okay, so the charging time constant is on-state resistance of PMOS into the capacitor CL, and the discharge time constant tau N is equal to on-state resistance of NMOS Rn into the capacitance CL. Now we can very well say that the rise time is proportional to this thing, and fall time is proportional to tau N. Okay, and that is what we want to do. We want to find out that why rise time and fall time are not coming equal when I use PMOS and NMOS with equal sizes. Okay, so for this we have to actually compute what is the mathematical modeling of the on-state resistance of a MOSFET? Yeah. So we can say T rise is RP into CL and T fall is RN into CL. So we can say T rise upon T fall is equal to RPCL upon RNCL equal to RP upon RN. Is it not? So we can say T rise upon T fall will be equal to 1 if RP upon Rn equal to 1. So rise time and fall times will be equal in CMOS inverter only if the onset resistance of PMOS is equal to onset resistance of NMOS. So now our question is this a fact? Is this true? Is this true? Okay. So we know that rise time upon fall time is equal to RP upon Rn. If RP was equal to Rn, then we should have got rise time equal to fall time, which we are not getting even in simulation. So we have to find out that if RP is not equal to Rn, because of which rise time is not coming equal to fall time, what can I do to make RP equal to Rn? So the necessary condition for rise time being equal to fall time is that RP should be equal to Rn. So we will find out. Okay. So is onset resistance of PMOS equal to onset resistance of NMOS? Now we go to MOSFET theory. Okay. Please note that when we are using PMOS and NMOS in a CMOS inverter, the MOSFETs are actually going into saturation. Please note this thing again. Okay. So we can say that since PMOS and NMOS are acting as switches, both of them enter into saturation or pinch off. Okay. Next is, now we told that is RP equal to Rn. The question is, what is the value, not a value, what is the mathematical modeling of MOSFETs onset resistance when in saturation? Okay. So what is the mathematical modeling of MOSFETs onset resistance when in saturation? It's here. So The device current IDS in saturation can be given as K dash into W by L into the gate to source voltage minus threshold voltage square. Okay, so the device current in saturation is K dash into W by L into VGS minus VT whole square, and K dash is actually equal to mu into Cox into W by L into VGS minus VT whole square. Again, Cox is given as mu into epsilon ox upon Tox into W by L into VGS minus VT whole square. So the device current in saturation is equal to mobility of the charge carriers into epsilon ox upon Tox into W upon L into VGS minus VT whole square. Okay. So we also know that the dynamic resistance, as you studied in second year, the dynamic resistance R is equal to deba V upon deba I. So in our case, we can say it is equal to 1 over deba I upon deba V, which is nothing but equal to 1 over deba IDS upon deba VDS. Okay, so there is no need of explaining this thing. This is proven already. Okay, so if we do the partial differentiation of the device current IDS with respect to VDS, and if we take a reciprocal of that, this is what we get. We get R on equal to 1 upon K dash into W upon L into VGS minus VT. Okay, so we can say relation 1, relation 2, relation 3, relation 4, relation 5, relationship 6, and relationship 7. So now we have put down that the onset resistance is equal to 1 over K dash into W by L into VGS minus VT. Is it not? And here, as I told you that K dash is mu into Cox, and Cox is equal to epsilon ox upon Tox. Okay, so I have to now replace K dash with the correct values. So which is equal to 1 over mu into epsilon ox upon Tox into W by L into VGS minus VT. This becomes my relationship 8. Now we have to write the same equation, that is we have to write equation number 8 for both PMOS and NMOS. So I will say rewriting equation number 8 for PMOS and NMOS devices, we can say RP is equal to 1 upon mobility of holes mu p. Now epsilon ox, okay, so epsilon ox is nothing but it is the permittivity of silicon oxide, which is equal to epsilon 0, that is absolute permittivity into relative permittivity of SiO2, which happens to be 3.9. okay, so as such epsilon ox is a constant now. Okay, it's a constant. So epsilon ox is nothing but the permittivity of SiO2 absolute into relative, like this, right? So epsilon ox is constant. So that is why we cannot say epsilon ox P. It is to be epsilon ox only. Okay, and oxide thickness is also same. Okay, so here we can say mu P into epsilon ox into T ox into width of PMOS upon length of PMOS, and we have VGSP minus VTP. This is equation number 9. Similarly, I will rewrite the equation for NMOS. Rn equal to 1 upon mobility of electrons into this term epsilon ox upon T ox, then width of NMOS upon length of NMOS into VGS N minus VTN. Equation number 10. Now we go back to this relationship that T rise will become equal to T fall only if RP is equal to RN. Okay, so now we have obtained the relationships between the onset resistance of MOSFET and the geometry of the MOSFET. Okay, so we have to say that to have T rise equal to T fall, we need RP equal to RN. Okay, so what I do is I take a ratio of both RP upon RN. Assuming similar operating conditions, we get RP upon Rn is equal to mu n upon mu p into Wn by Ln upon Wp by Lp. Now we are coming to one very important step, so you should please pay attention. Okay. Okay. Now we already told that Wn by Ln is equal to P and Wp by Lp is equal to P, but we will not put it at this time. Okay. Now see here, we had made this statement. So from equation number 3, so we can say this is equation number 11. From equation number 3, Lp equal to Ln equal to L. Therefore, Rp upon Rn is equal to mu n upon mu p into Wn, sorry, okay, this is relationship number 12. So the ratio of resistances of PMOS and NMOS is equal to the ratio of mobilities of electron to hole multiplied by the ratio of width of NMOS to PMOS. Now all of you must be aware of this fact that from semiconductor physics we know that mobility of electron is approximately 2.5 times the mobility of holes. This is proven. Okay, so what we do is that we substitute this relationship in equation number 12. Okay, what we get is Rp upon Rn is equal to 2.5 times into Wn by Wp. This is equation number 14. Right? Again, third time I am repeating, to have T rise equal to T fall, RP should be equal to RN. Okay, or we can say RP upon Rn equal to 1. So equating equation number 14 to 1, what we get is this: 2.5 times Wn upon Wp equal to 1. Therefore Wp by Wn should be equal to 2.5. Okay, so this is our conclusion. And all of you know that Wp is width of PMOS and Wn is width of NMOS. Or we can also say that Wp is equal to Wn, or we can say PMOS should be 2.5 times wider than okay. So based on all this mathematical analysis, we have concluded that the rise time and fall time of a CMOS inverter will only be possible if I use wider PMOSs than NMOSs. Okay, PMOS should be 2.5 times wider than NMOS. Now somebody may say, sir, do you have any statistics? Yes, we do have statistics. So if you read, or if you ask Google or go to Wikipedia, then we know that in silicon material, it is found that mobility of electrons is found to be 650 centimeter square per voltage second, and mobility of holes is 270 centimeter square per volt second. So if we see, the ratio of mobilities comes out to be 650 upon 270, approximately 2.41. It comes out to be approximately 2.41. So it is sometimes said it is 2 to 3. Fine. Now somebody may tell that, sir, do you have any proof that if I keep the width of a PMOS 2.5 times width of NMOS, then what is the rise time variation? So this is where it is. So if you can see this Excel sheet, so what I have done is that I have written a SPICE program. SPICE is a special language. It stands for Simulation Program with IC Emphasis. So I wrote a SPICE program for a CMOS inverter, and in that program I told the program to find the rise time and fall times of a CMOS inverter, and this is what I have got. So what I did is that I took different W bell ratios. So I saw the first column, that is column A, is actually relative size of PMOS and NMOS. So you see there it is WP by LP, which is actually small p or size of NMOS, and denominator is WN by LN, that is the size of NMOS. So basically column number A is P upon N. So I kept P upon N equal to 1. So when I used equal size MOSFETs, I got propagation delay as 0.628 picoseconds, and rise time and fall time were 34.26 and 26.05. So there was a 31.5% error between rise time and fall time. So there was a 31.5% error between rise time and fall time if I took equal size MOSFETs. Then I increased the relative size from 1 to 1.5, and then I got the error as minus 1.8%. And when I took PMOS 2.5 times larger than NMOS, in the sense when I say larger means the lengths remain the same but the widths vary. So when I took the width of PMOS 2.5 times that of NMOS, you see the rise time and fall times 28.785 versus 28.764. So I got an error of only 0.1% between rise time and fall times when I made PMOS 2.5 times wider than NMOS. Then I again deviated from 2.5 to 3, and again you see I got again an error of minus 1.8%. As and when I am deviating from the relative size of 2.5, I am getting increasing percentage error between rise time and fall time. So this proves, the SPICE program simulation proves that if I want comparable rise and fall times in a CMOS inverter, my PMOS should be always larger. Now somebody may tell us how to design. So let us design a CMOS inverter. So many a times such numericals can be asked. So numerical is like this. Okay. Design a CMOS inverter to have rise time equal to fall time for 120 nanometer process. Okay. So the question is, design a CMOS inverter to have rise time equal to fall time for 120 nanometer process. So the solution goes something like this. So I have my CMOS inverter, and this is my PMOS, and this is my NMOS. Okay, and here what I do is that I simply write down WP by LP, and here I write down WN by LN. So please note that whenever there is a design numerical, it is expected that we find out the values of WP, LP, WN and LN. So designing a CMOS inverter to have equal rise and fall times means actually finding out the widths and lengths of the constituent PMOS and NMOS devices. So see, there are certain axioms involved in this solution. The first axiom is this, as we told. So understand that this 120 nanometer is actually the value of L. Okay, and as already told, and already we have told here that LP is equal to Ln equal to L in equation number 3. Okay, so in equation number 3, we are told that LP is equal to Ln equal to L. So in the numerical, this value 120 nanometer is actually to be taken as L. So that is why I'll write down that L given L equal to 120 nanometers. Okay. Second fact is LP equal to Ln equal to L equal to 120 nanometer. That means what? Out of these 4 parameters, already the value of LP and Ln is given already. So LP and Ln automatically become 120 nanometer because the process is 120 nanometer. Okay. Now, third important step is this, that for reliable operation of NMOS device, this is a semiconductor physics factor. So for reliable operation of NMOS device, the size of NMOS N, which is equal to Wn upon Ln, should be equal to 1.5. So this is what you have to remember. So for reliable operation of NMOS, the size of NMOS should be equal to 1.5, right? So already the value of Ln is known. Okay, so N equal to 1.5 equal to Wn by Ln, and you know that Ln is equal to 120 Wn upon 120 nanometers. Therefore, Wn, the width of NMOS, is 1.5 times Ln, which comes out to be 180 nanometers, right? So using the fact that the size of NMOS for a reliable operation is 1.5, we have ended up with the value of Wn also. So out of 4 parameters, Wp, Lp, Wn, Ln, LP and Ln are already given in the numerical. Using n equal to 1.5, we are able to find the value of Wn. Now the question comes, what about the value of Wp? So already in the whole discussion, we already told that Wp should be 2.5 times Wn. Okay, then we write, but the width of PMOS is 2.5 times the width of NMOS for rise time equal to fall time. Therefore, Wp is 2.5 times 180 nanometers, which comes out to be 180 into 2.5. It's 450 nanometers. So our design is over. So after calculating these values, that is Wn equal to 180 nanometers, Wp equal to 450 nanometers, and Lp equal to Ln equal to 120 nanometers, the solution comes like this, that this is how you are expected to express the solution. So now we have to write down here 450 upon 120, and here you have to write down 180, 120. Very important thing. See now, what are the sizes? Now you can actually do reverse engineering and find out, have we followed the concept of device sizing? So 450 upon 120, that it is Wp by Lp equal to P. It is now equal to 3.75. 180 by 120 is Wn by Ln, N, which is equal to 1.5. And the relative size is now equal to 2.5. Okay, so the size of PMOS is 3.75, the size of NMOS is 1.5, and the relative size is 2.5. In Viva, almost every student gets confused when I ask a student, so what is the size of PMOS? He says size of PMOS is 3.75. I don't know. The size of PMOS is 3.75, size of NMOS is 1.5, and the relative size is 2.5. That is why when I ask a question to the student, what is the significance of the number 2.5 in having equal rise and fall time, student gets confused. That is why I will write it here. This is the summary. To have rise time equal to fall time in a CMOS inverter, first size of PMOS is equal to 3.75. Second fact is size of NMOS is equal to 1.5. The third fact is relative size is equal to, so this is equal to P, this is equal to N, and relative size is equal to P upon N is equal to 3.75 upon 1.5 equal to 2.5. Size of PMOS is 3.75. Size of NMOS is 1.5 and the relative size is 2.5. Okay. Now, as far as the syllabus is concerned, I was planning to finish body effect, but somehow I spent more time, but it was worth. I think so we'll be able to wind up the unit number 4 in next week.